Hello everyone. Today my chapter is Nitro compounds. Introduction. Nitro compounds are an important class of organic compounds which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atom by nitro groups. Nitroarenes. Example: nitro compound in which NO2 group is directly attached to benzene ring can be prepared rather easily and have been used as synthetic reagent since long, but nowadays even nitroalkenes are being prepared and used on a large scale. Structure of nitro group. Nitro group is quite often represented as containing a double bond between nitrogen and one more oxygen, and a coordinate or rotative bond between nitrogen and other oxygen, or but actually nitro group is established by resonance and is a hybrid of equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that the bond length of its nitrogen-oxygen bond is 121 pm or 1.221 angstrom, which is intermediate between NO single bond length 136 pm or 1.36 angstrom and NO double bond length 115 pm or 1.15 angstrom. In case of nitroarene, resonance of nitro group with the ring can also take place, giving rise to additional contributing structure for the molecule. It will be interesting to note that nitro group is isoelectronic with carboxylate anion. Nomenclature of nitro compound. Nitro compound named by writing the word nitro before the name of the parent compound. The number of nitro group and their position are also stably indicated as illustrated below. Nitromethane, nitroethane, 2-nitropropane, 2-nitro, 3-methyl-butane. Classification of nitroalkane. Nitroalkane are termed as primary, secondary or tertiary according to as the nitro group is attached to a primary, secondary or tertiary carbon atom, that is primary nitroalkane, secondary nitroalkane, tertiary nitroalkane. Primary nitroalkane example is nitroethane. Secondary nitroalkane example is 2-nitropropane. Tertiary nitroalkane example is 2-methyl-2-nitropropane. Preparation of nitro compounds. Preparation of nitroalkanes. Nitroalkanes are usually prepared by the following methods. First is vapor phase nitration of alkanes. This reaction involves the substitution of a hydrogen atom of the alkane by a nitro group. It is carried out in the vapor state by heating the alkane with nitric acid at about 700 K. Reaction is alkane will form nitroalkane plus water under the temperature of 700 Kelvin. Limitation of the process. During nitration of higher alkane, all possible isomeric nitro products are formed. Moreover, rupture of carbon-carbon bonds also take place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane results in the formation of a mixture of 4 nitro compound as shown in. Due to the formation of complex mixture of product, this method is not used for the laboratory preparation of nitroalkane. However, the method is widely used for the commercial preparation of nitroalkanes, since they are used as industrial solvent only. Propane will form 1-nitropropane plus 2-nitropropane under HNO in the reaction of HNO3 and 673 Kelvin pressure, and also formed nitroethane plus nitromethane. Mechanism. The reaction is believed to involve the formation of free radicals, but the mechanism is not well established. Second is action of silver nitrite on alkyl halide. This is the method generally employed for the laboratory preparation of nitroalkanes. When heated with silver nitrite, alkyl halide undergo nucleophilic substitution to form nitroalkanes along with small quantities of alkyl nitrite. This is because NO2 is an ambident nucleophile. Alkyl halide plus AgNO2 will form the nitroalkane plus alkyl nitrite plus AgBr. Nitroalkane is major product, alkyl nitrite will be minor product. However, the mixture of alkyl nitrite and nitroalkane can be separated by fractional distillation. Third is oxidation of amines. When an amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Amine will form tertiary nitroalkane in the presence of KMNO4. Preparation of nitroarene. Nitroarene are almost invariably prepared by the direct nitration of arene. The nitrating agent generally used are: first is concentrated or fuming nitric acid, second mixture of concentrated or fuming nitric acid and concentrated sulfuric acid. Sometimes fuming sulfuric acid is also used. This mixture is the most commonly used as nitrating agent. Third is mixture of concentrated nitric acid and acetic anhydride or boron trifluoride. Fourth is acetyl nitrate obtained by mixing nitrogen pentoxide and acetic anhydride. Fifth is nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent to be used for nitration of a given compound depend upon the following two factors. First is nature of compound to be nitrated. Second is number of nitro group to be introduced. In the nitration of aromatic compound containing electron releasing or activating groups such as NH2OH, CH3, the reaction takes place readily at room temperature by employing concentrated HNO3. In some cases, even dilute HNO4 can be used. For example, phenol plus dilute HNO3 will form ortho and para nitrophenols plus water. For nitrating compound containing electron attracting or deactivating groups such as COH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. It may be remembered that nitro group itself is also a deactivating group. Nitrobenzene and dinitrobenzene, for instance, can be obtained from benzene under the condition given below. Now the mechanism of nitration. Nitration of aromatic compound like other aromatic substitution reaction is electrophilic in nature and involve a nitronium ion NO2 positive as the attacking electrophile. The mechanism may be summed up as below, followed by considering the nitration of benzene with nitric acid sulfuric acid mixture. First is generation of electrophile. HONO2 plus 2H2SO4 will formed NO2 positive. Nitronium ion plus H3O positive plus 2HSO4 negative. Second is formation of carbocation ion. Third is proton transfer from the carbocation to yield the final product. Now, evidence in favor of the above mechanism. It has been shown that the aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as the electrophilic reagent, is generated in a preliminary step and brings about further reaction in two steps. The first step is a slow rate determining step involving the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. This mechanism has been fully supported by the isotope tracer technique as explained below. If an aromatic compound labeled with deuterium, the heavier isotope of hydrogen having a mass of 2 AMU is subjected to nitration, it is found that the rate of substitution of deuterium is the same as that of ordinary hydrogen or protium. In other words, no isotope effect is observed. Since carbon deuterium bond is broken more slowly than a carbon protium bond, the absence of isotope effect in aromatic nitration can be justified only if the rate determining step of the reaction does not involve any cleavage of carbon-hydrogen bond. This means that the final step involving the abstraction of proton through the cleavage of carbon-hydrogen bond cannot be the rate determining step. Therefore, the step leading to the formation of carbocation must be the rate determining step, as it does not involve any cleavage of carbon-hydrogen bond. Once formed, the carbocation loses the proton relatively fast to form the final product. The absence of isotope effect also rules out the possibility of a single-step mechanism for nitration. This is because single-step substitution cannot take place without the cleavage of carbon-hydrogen bond. As such, it must exhibit isotope effect, but this is not so in actual practice. Hence, aromatic nitration is a stepwise process in which the formation of carbocation is a rate determining step. Comparison of nitration of arene and nitration of alkanes. It may be noted that nitration of arenes take place at comparatively relatively low temperature, whereas nitration of alkanes require a very high temperature. This may be due to the fact that nitration of arene involves the initial formation of an electrophilic reagent, while the nitration of alkane is supposed to involve the initial formation of a free radical. The formation of free radical takes place through homolysis and requires stronger condition than the formation of electrophile, which takes place through hydrolysis. As such, nitration of arene takes place more easily than the nitration of alkanes. Nitroarenes cannot be prepared by the action of silver nitride on aryl halide because of the very low reactivity of aryl halide toward nucleophilic reagent. Physical properties of nitro compounds. First is physical state. Nitroalkanes are colorless, oily liquids when pure. They have pleasant smell and are sparingly soluble in water, with the exception of a few compounds including nitrobenzene, which are yellow oily liquids. Till other aromatic nitro compounds are yellow crystalline solid. Nitrobenzene has an odor of bitter almond and is known as oil of myrrhine. Solubility and density. All the nitro compounds are heavier than water. Nitroalkanes are sparingly soluble in water, while aromatic nitro compounds are soluble in it. They are, however, readily soluble in organic solvents such as alcohol and ether. Third is stability. When heated strongly, polynitro compound decompose with explosive violence. Fourth is boiling point. Due to the presence of highly polar nitro group in their molecule, nitro compound have strong dipole-dipole interaction. Consequently, they possess high boiling point, much higher than hydrocarbon of comparable molecular masses. However, most of the nitro compounds are volatile in steam. The melting and boiling point of nitro compound gradually increase with the number of nitro group as illustrated ahead. Nitrobenzene melting point is 278.8 Kelvin and boiling point is 463 Kelvin. Metadinitrobenzene melting point is 363 Kelvin and boiling point is 576 Kelvin. 135 trinitrobenzene melting point is 395 Kelvin. Now the chemical reaction of nitroalkanes. The important chemical reaction of nitroalkane are as follows. First is acidic nature, tautomerism. Nitroalkane containing alpha hydrogen atom, example primary and secondary nitroalkane only, exhibit acidic behavior and form salt in the presence of strong alkalis. For example, RCH2NO2 plus NaOH. This will form the RCHNO2 negative Na positive plus H2O. The acidity can be attributed to the fact that nitro group has a strong electron withdrawing inductive effect minus I effect. The anion formed after the removal of the proton from nitroalkane get resonance stabilized due to the ability of the nitro group to accommodate negative charge. It is interesting to note that if the salt formed by nitroalkane is acidified at low temperature, the oily drops of nitroalkane do not separate immediately, but we get another form of nitroalkane known as acinitroform, which slowly changes into the nitroform. This is due to the fact that primary and secondary nitroalkane exhibit tautomerism, the tautomerism form being nitrorhizoform and acinitroform. The tautomeric equilibrium between the two forms lies almost completely towards the nitroform because it is stabilized by the resonance of nitro group. Acinitroform is relatively stronger acid than nitroform. An important feature of acinitroform is that it can act both as an electrophile and a nucleophile. Unlike primary and secondary nitroalkane, tertiary nitroalkane and nitroarene do not have any alpha hydrogen atom. As such, they exhibit neither acidic character nor tautomerism. Reduction of nitroalkane. Reduction of nitro compound is one of the most important reactions. The reduction of nitro group takes place in stages as given shown below. Nitro compound will form the nitroso compound, which will form the substituted hydroxylamine, and it will form the primary amine. The product actually obtained depend upon the nature of the reducing agent and the pH of the reaction medium. Thus, nitroalkane can form different product on reduction as given below. First is reduction in acidic medium. When reduced in an acidic solution, nitroalkane form primary amine. Nitroalkane plus 6H. This will form the primary amine plus 2H2O. Second is catalytic reduction on reduction with LiAlH4. Reduction with LiAlH4H2 in the presence of nickel palladium or platinum catalyst also yield the same product. Reduction in neutral medium. If the reaction is carried out in a neutral solution, a hydroxylamine derivative is obtained. The hydroxylamine are readily oxidized to corresponding nitroso compound on warming with toluene reagent, which get reduced to metallic silver. This reaction is used as a test for nitro compound under the name Baker-Millikan test. Third is hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkane undergo hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine. For example, nitroalkane plus H2O plus HCl, when it is heated, this will form the RCOH plus NH2OH.HCl. Secondly, nitroalkane are hydrolyzed to ketone and nitrous oxide by boiling with concentrated HCl. Tertiary nitroalkane and nitroarene are not hydrolyzed by acid. Fourth is NAF reaction. When sodium salt of primary and secondary nitroalkane are hydrolyzed by boiling with dilute sulfuric acid, aldehyde and ketone respectively are obtained. The reaction proceeds through the AC-nitro form of nitroalkanes. In this reaction, the AC-nitro form acts as an electrophile. Fifth is action with nitrous acid. Primary, secondary and tertiary nitroalkane exhibit different behavior toward nitrous acid. Primary nitroalkane react with nitrous acid to form nitroleic acid, which dissolve in NaOH to produce a red solution. Secondary nitroalkane react with nitrous acid to form nitrols which have blue color but do not dissolve in NaOH. Tertiary nitroalkane and nitroarene do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction can be used for distinguishing between primary, secondary and tertiary nitro compound. Sixth is halogenation. When treated with halogen, chlorine or bromine in slightly alkaline solution, primary and secondary nitroalkane undergoes halogenation at alpha position. Nitromethane on chlorination in alkaline medium giving trichloronitromethane, also known as chloropicrin. Tertiary nitroalkane do not undergo halogenation because they do not have alpha hydrogen. Seventh is condensation with aldehyde. Due to the presence of active alpha hydrogen atom in them, primary and secondary nitroalkane undergoes aldol type condensation with aldehyde in the presence of a base to form nitroalcohols. Acetaldehyde plus nitroethane, this will form the 3-nitro-2-butanol. The reaction proceeds through the AC-nitro form, which act as a nucleophile in this reaction. Eighth is Mannich reaction. This is a condensation reaction which involves formaldehyde, ammonia, or a primary or secondary amine, and a compound having at least one active hydrogen, such as primary and secondary nitroalkanes. For example, secondary nitroalkane plus HCHO plus NH4Cl will form nitroamine hydrochloride. The reaction can be used for preparing nitroamine, diamine, etc. Chemical reaction of nitroarenes. Nitroarenes are chemically rather inert compounds. The nitro group is firmly attached to the nucleus and cannot be replaced by the atom or group under ordinary conditions. Their important reactions are as follows. First is acidic nature. Unlike primary and secondary nitroalkanes, nitroarenes do not have any alpha hydrogen atom. As such, they do not exhibit acidic character or tautomerism. However, nitro compound having two or more nitro group attached to the benzene ring are somewhat acidic in nature due to the strong electron withdrawing group of the nitro group on the benzene ring. Second is reduction. The most significant reaction of nitro compound in their reduction under different conditions to give different product. As already stated, the reaction take place in stages and the nature of the final product depend mainly on the pH of the reaction mixture. We will illustrate the reduction of nitroarene under different conditions with the help of nitrobenzene. Third is reduction in acidic medium. On reduction in acidic medium with an active metal and acid such as zinc and HCl or tin and HCl, nitrobenzene yield aniline. Nitrobenzene will form aniline plus 2 water molecule in the presence of Zn, या HCl or SN or HCl. Mechanism. The mechanism proposed for the reaction involves a number of steps in which addition of electron and proton take place and nitrobenzene free radical anion and nitrosobenzene free radical anion are formed as intermediates. Catalytic reduction. Reduction of nitrobenzene with H2O in presence of nickel or platinum catalyst also leads to the formation of aniline. Third is Reduction in neutral medium. When reduced in a neutral medium, example with zinc dust and ammonium chloride solution, the reaction stop at the hydroxylamine stages. Reduction in alkaline medium. On reduction in alkaline medium, nitrobenzene yield different product depending upon the nature of the reducing agent employed. These products are actually formed by the further reaction between the primary reaction product, example nitrosobenzene and phenyl hydroxylamine, as shown in. Azoxybenzene is formed by a condensation of nitrosobenzene and phenyl hydroxylamine, as given in. There is sufficient evidence to show that azobenzene is formed through the intermediate formation of azoxybenzene and its further reduction. Hydrazobenzene C is similar by the further reduction of azobenzene. Reduction with LiAlH4. Reduction of nitrobenzene with LiAlH4 also yield azobenzene. Electrolytic reduction. When reduced electrolytically in a weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic solution, nitrobenzene yield para-aminophenol due to the rearrangement of phenyl hydroxylamine first formed. Electrolytic reduction in alkaline medium yield azoxybenzene, azobenzene, and hydrazobenzene. Selective reduction. In case of compound containing more than one nitro group, it is possible to carry out the selective reduction of one of the group by employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide Na2SX. This reduction is known as renin reduction. Third is electrophilic substitution. Nitro group being an electron withdrawing group has a strongly deactivating effect on electrophilic substitution reaction of benzene nucleus. However, under strong conditions, nitro compound may undergo electrophilic substitution in meta position with respect to the nitro group. It may be noted that nitrobenzene does not undergo Friedel-Crafts reaction. Fourth is nucleophilic substitution. The nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to the electron withdrawing nature, but this very electron withdrawing influence of the nitro group make the benzene nucleus liable can be attacked by nucleophilic reagent. Thus, unlike benzene, nitrobenzene or heating with sodium hydroxide gives a small amount of ortho and para-nitrophenols. Mechanism. The mechanism of the reaction may be outlined as followed by considering the formation of para-nitrophenol. Fifth is replacement of the nitro group. In case of polynitro compound, one of the nitro group itself can be replaced by nucleophilic groups. Thank you.